All right, so let's take a look at the warm-up up here. We're given a matrix A, and we're given a vector B. And the first question is B in the column space of A. So what does it mean to be in the column space of A? What's our definition for column space here?
Linear combinations of A.
Linear combination of the columns of A, absolutely. So we have two columns, this one and this one. If I want to find out, is there a linear combination of those two columns that brings me to B? I could say, is there an x1, some number times the first column, plus some number times the second column? That would give me 1, 5. That's kind of the question. Of course, that's the vector equation, which is really the same as the matrix equation, which is the same as the linear system. And to figure out if there is an x1 or x2, we could just solve the augmented system. So that's what we'll do here. We'll take that thing, we'll do a little row reduction. I'll kind of zip through it pretty quickly here. That's what I get. Anyone else confirm that? Confirm or deny? Please confirm. You know my steps are sometimes sketchy. Right? Okay. So that tells me that there is an x1 and x2. There is some linear combination of the columns that get me to 1, 5. So in this case, yes, B is in the column space of A. Now, did I have to do all that work? Is there anything I could have done right away at the beginning to confirm that it was in the column space of A?
It's not you're checking in the R1, it's an R2.
I'm checking what?
An R1 is an R2. So.
All right, I think we're going with R2, right? Our B here is a vector in R2, and our column space must be at least a subspace of R2, right? Because we take a linear combination of R2 vectors, the result must be some of R2, maybe all of R2, but certainly a subspace of R2. So then the question, is it a subspace of R2, or is it all of R2? Well, how many linearly independent vectors do I need to get all of the vectors in R2? 2. And are these linearly independent? They are, right? I can just check. If I have 2 vectors, I can just see if they're multiples of each other. They're not multiples of each other. So these are linearly independent. So they must span all of R2. So can I get to this vector? Sure. I can get to all the vectors. So I can actually kind of argue that without doing any work from the beginning. But in general, the process would be to solve the system and find the linear combination that would get us to 1, 5. Okay. The next one, describe the null space of A. What is the null space again?
A says
AX equal to solution.
Absolutely. It's all the x's that get mapped to 0. All right, so we look at AX equals 0. It's all of the x's that we plug in here to satisfy this equation. Well, we've done a lot of the legwork here. You know, if we didn't augment with this right-hand side, we would have started with just this matrix, and that would have row reduced to this matrix. And so what does that tell us about the solutions to AX equals 0, and that's 0 vector? So what would the solutions be, though? How many solutions are there? One solution. What is the solution? The trivial solution. There's always one solution to the homogeneous equation, the trivial solution. The x equals 0, 0 solution. Since this thing row reduces to identity here, there's only one solution. There are no free variables. So this is the only solution. So this is the null space. Wait a second. The null space is 0? Is that even a space? Well, to be a subspace, if we take a little set of all the vectors from R2, we grab a certain collection of those vectors. Here my collection is very small. It's just the 0 vector. But does it satisfy the 3 properties that make a subspace? Does it contain the 0 vector? That's the only vector, right? It's definitely got that. Is it closed under addition? I only have one vector to add, 0. If I take 0 plus 0, am I still in my set of 0? I am. And if I multiply that 0 by anything, I get 0. I'm still in that space. So it is closed under scalar multiplication as well. So this is my null space. It is a space. All is right with the world. All right, any questions about the warm-up? All right, plan for today. Plan for today is to finish up 2.8 and 2.9. We got most of the way through 2.8, but we still have to talk about what a basis is. So then we want to be able to describe the things we know, these spaces we know in terms of a basis. Find the dimension and the rank. These are things we're going to talk about in 2.9. And talk about coordinate systems. So those are the big ideas that we're going to talk about today. For Thursday, we are going to begin section 4.4. We're going to do a little jumping around from this point. We're going to jump to 4.4, which is the one section we're going to cover from chapter 4. I'm going to mix a little bit of 4.7 in there as well. Because once again, as we talked about yesterday, 2.8 and 2.9 kind of summarize chapter 4. We're going to do one section from chapter 4, and then we're going to go to 2 sections from chapter 3, and then we're going to launch into chapter 5, which is where we really want to do most of the work for the rest of the semester. There will also be a quiz tomorrow on the lingering ideas from chapter 2. So mostly 2.8, 2.9, but a little bit of that inverse matrix stuff as well. One other administrative point here. There were still some questions about that number 10 from 2.3 we weren't all the way happy with. I'm going to score those correct for everyone. I just have to figure out how to do it in this homework system. So instead of going through each person and changing their score, usually there's a global way to do it. Just not familiar how to do it, but I will change those. So don't stress on whether you got that one right or wrong. All right, any questions at all? All right. So from last time, we talked about all this stuff. A riveting class. You were on the edge of your seats all class period, I could tell. I know, yesterday was kind of a boring class. There was a lot of lecture. We're going to try to be a little more interactive today. Then your algebra is just a lot of definitions we have to master. That's kind of the problem. Well, we started off with vector space. It was a set of elements where we defined addition and multiplication, and they had to satisfy those big 10 properties. That was our vector space. Talking about subspaces, it was a subset of the elements, and because it already satisfied most of the properties, we only had to check our 3 here. Is the 0 in the space? Is it closed under addition? Is it closed under scalar multiplication? And then we defined our column space and null space. We just practiced that in the warm-up. And the last thing we needed to get to was the idea of a basis. A basis is a set of linearly independent vectors that span a space. It's the building blocks of a space. And because this is a set of vectors that span the space, that means I can take a linear combination of them to get anywhere in the space. So they can generate the entire space, if you will. So let's look at these 2 kind of key points here. So 2 key points of this definition. 1, they span the space. So that means any vector in the space can be written as a linear combination of the basis vectors. Or you have this little group of basis vectors, and you say, you need to get to this vector. Oh yeah, it's 2 of these, 1 of those, 3 of these. There's always a way you can do that because they span the space. But the vectors are also linearly independent. That tells us that when you find the directions to get to that vector, they are the only directions. There is only one linear combination that can get you to that vector. There is no redundancy in our vectors. Right? None of the vectors in our set, in our basis, are a linear combination of the other ones. There are unique directions to our other vectors. There's a unique linear combination that gets us to a vector. So if we're given a set of vectors, we should be able to determine whether they're a basis or not. We have to see, are they linearly independent? And do they span the space? So those are not new ideas, so we should be able to test for those ideas. So, is this a basis for R2? And we're going to do a clicker quiz on this. So get out your clickers. I'm going to start this. Let's see where we're all at. I'll give you a little time to do some work if you need to do some work on this.
So A, yes, B, no.
Yep. A, yes, B, no. There'll be a lot of yes or no questions today, so A, yes, B, no for all of the questions for today. We have about 16 people in here. Anybody not have a clicker today? One. Anybody else? 16, 12, 14, 16. 6, 10, 12, 14, 16, 18. I should have 17. Let's see what it looks like so far here. All right, most people saying it is a basis. A couple people saying it's not a basis. Okay, to check if it's a basis, we have to have two things. One, does it span R2? Can I get everywhere I want to in R2? Well, to answer both of these questions, actually, I can grab this thing and turn it into a little matrix. And then I can row reduce this thing. We'll save the row reduction steps, and I'll just jump to the exciting conclusion. There it is. That's the row reduced form. So how does that row reduced form tell me whether or not this spans the space?
Free variable.
The free variable doesn't necessarily tell me it spans the space, though. I could have free variables in a system like this and still have it not span the space. When I ask if it spans the space, I'm really saying, is it onto? Is it onto? And if it's onto, what's true about this row reduced form?
Pivot in every time.
Pivot in every row. So to find out if this thing spans R2, I need to find out if it has a pivot position in every row. And it does have a pivot position in every row. And it does span R2. Now to find out if it's linearly independent, then what do I need? That's the same thing as saying, is it one-to-one? So there I need a pivot position in every column. I don't have a pivot position in every column. I have a pivot position in this column and this column. And in fact, what that tells me is I can use that information to find the linearly independent columns of the original matrix. So the fact that my pivot position is in the first column and the second column tells me that these first two vectors are linearly independent. And that means I can take a linear combination of these two to get to this one. Now, a lot of people will do the reduction and grab these two vectors. So, yep, these ones will span this space. These two are linearly independent. That's actually true in this case, but it's not going to answer the question in all cases. So in other words, you might get vectors here that aren't necessarily in the span of here. So when you go to find out, is this a basis? I want to find a basis. I want to find a set of linearly independent. You grab them, you throw them in a matrix, you do the row reduction, and these pivot positions mark the columns of this matrix that you're going to grab. So this tells me grab the first vector, this one, and grab the second vector, this one. These two will form a basis. These two are going to be onto, in this case, they're going to span it, and these two are going to be linearly independent. Okay. Let me say that one more time. Once we've determined it's onto, we want to find the linearly independent vectors, then we'll use that reduced version to grab those columns. Okay. So, is this one a basis? The set of 3 here? It is not a basis, because those 3 vectors are not linearly independent. This would be a basis. But the 3 vectors are redundant. I have an extra one in there. That set of 3 vectors is not linearly independent. Questions about that? So this would be a basis for R2. All right, let me stop that one. Let's try another one here. Let's look at this one. All right, I have a matrix A. I have done the row reduction. Is this the same matrix? Yeah, it's the same matrix. All right, let's just use it to answer different questions. So, same matrix. Row reduced form is the same. What is the column space of A? So this is not a clicker question here. What is the column space of A? Those one might be a little tricky to express. We're going to need a little bit of notation to express this. But what's the definition of the column space of A?
Set of all outputs possible.
Absolutely. It's the set of all possible outputs. It's the span of the columns of A. Well, in the last problem, we found out that this transformation was onto. That actually the span was all of R2. So in this case, the column space of A is equal to R2. Now that's a nice way to write that one because it's all of R2. If it wasn't all of R2, if it was some subset of R2, some subspace of R2, subspace, I have to find a way to describe that space. One way I can subscribe it is in terms of its basis vectors. I can say it's a linear combination of its basis vectors. So in this case, I could say it's the span of, and I don't need to say 1, 1, 2, 1, 1, 0. I could just say it's the span of 1, 1 and 2, 1. That would also be the column space. In this case, that's equal to R2. Why don't I need to say the span of 1, 1, 2, 1, and 0, 1? It's redundant. It's not that it's not true. It really is the span of all 3 of those. Right? But right, I'm saying an extra thing there. I don't need to say that. All right, so what about the second one? Let me stop this thing. Let me start it again just to make sure we're clear on this point. Do the columns of A form a basis for the column space here? Okay, mostly no, but a couple of yeses still. All right, these three vectors can't be a basis because they're not linearly independent. Right, we have to only grab these two to make them a basis. Okay, so that would be no, it's not a basis. And what would be a basis? Just these two. Okay, let's try one more here. Is this one a basis for R3? All right, most people saying no. Why not? Why is it not a basis, just those two vectors?
Third vector is multiple of the first
Well, let's just stick with those two. Before I added my third one, if I just had those two.
one. You don't have a
I don't have a pivot in every row. I don't have enough vectors. I have 3 rows, but since I only have 2 columns, I can only have 2 pivot positions. So I don't have a pivot for every row, which means what? It's not onto. It doesn't span all of R3. So now I add a new column. Now I have 3 of them. Now maybe I can span R3. But the problem was, as you mentioned, it's just a multiple of the other one. And once again, to determine this, I could just grab all these vectors, throw them into a matrix, and do my row reduction. So that's what I'm going to do here real quick. 1, 1, 2. I'll put my 0 on the bottom. I'll take this row minus this row. I will get 0, negative 1, 0. That's really good enough here. I have my 2 pivot positions. So now I want to find a basis from these 3 vectors. Is this a basis? We said no. We said no because in this case they're not linearly independent. Right, I have an extra one. So what would be a basis?
Positions are a pivot question.
Okay, so it could say, well, I have an extra one. Let's throw one of them out. And then I'll have a smaller space here. I'll have two linearly independent vectors. But the idea here is to do that, I would have to just grab these first 2. Right? Remember, if I look at this, it says grab the first column and the second column. That's where my pivot positions are. Okay? And then, we really want to understand that this is just telling me which ones are linearly independent. I still need to grab these 2 vectors, not these 2 vectors. If you think about the span of these 2 vectors compared to the span of these 2 vectors, it's going to be different. So this process is just marking the correct columns. Okay. That process. Okay. All right, so not a span because they weren't onto R3. And then when I added another vector, they weren't linearly independent. Okay. Now, right away, we said there weren't going to be enough pivot positions for every row because we only had 2 vectors. We really need 3 columns to have a pivot position for every row here. So in general, there's going to be a right number of basis vectors. Right? We can't have too few. We can't have too many. Right? If we want to span R3, we need at least 3 vectors. We could have 4, 5, 6, or 7 to span R3, but we need at least 3. We can't have less than 3. At the same time, if we have 4, 5, 6, or 7, some of those have to be redundant. So if we have R3, it takes exactly 3 vectors to span and be linearly independent. So there is a perfect number of basis vectors. So that's our two big points here. Pivot positions are going to identify our linearly independent columns. That's how we're going to find which ones are linearly independent. And there is also a perfect number of basis vectors for a space. And we're going to call that number the dimension of the space. So I've used this word before. We kind of say, okay, three-dimensional vectors, R3. We've said dimension a bunch of times. But now we have a more formal definition for it. The dimensions of a space is the number of vectors in its basis. So if three linearly independent vectors span a space, I'll call it the space V, then the dimensions of V, and that's how we write it as dim of the space, is equal to 3. In some sense, it's telling us the size of the space. And it lets me compare spaces. What's the dimensions of R3? What are the dimensions of R3? How many vectors do I need in a basis for R3? 3. How many dimensions do I need for R2? Or what's the dimension of R2? 2. How many vectors are in R3? Infinitely many. I mean, just in the space. How many vectors are in R2? Infinitely many. But intuitively, we understand that R3 is bigger than R2. One's the plane, one's three-dimensional space. This kind of gives us a sense of why one's bigger. Right? It has a bigger basis. Okay. All right, so if I have a space with dimension 3, then it takes exactly 3 linearly independent vectors to span the space. So if the dimensions of V is 3, and I have 2 vectors, could those vectors be linearly independent? Clicker quiz, yes or no? Linearly independent? Question mark. Could they be linearly independent? What does it mean to be linearly independent?
Scales of each other.
They're not multiples of each other for 2 vectors, or if there's more vectors, they're not linear combinations of the other. So if I grab 2 vectors in a 3-dimensional space, 1, 2, 4, and 1, 0, 1, could they be linearly independent? Sure. Absolutely. No restrictions on that. Could they span the space? Could they span the space? It's a little stronger result. No, they can't span the space. I need 3 to span the space. Okay. If I have 4 vectors, could they be linearly independent in this 3-dimensional space? Could they be linearly independent? No, they can't be linearly independent. So in other words, if the dimensions are 3, that means there's 3 elements in the basis. I can find 3 vectors that are linearly independent that span the space. I can take 3 vectors and have a linear combination that gets me to any other vector in the space. So if you give me 4 vectors in the space, one of them for sure has to be redundant. There might be more that are redundant, but one of them for sure has to be. All right, and for my 4 vectors, could they span the space? They could span the space. They might not span the space, but they could. All right, questions about that kind of back and forth with those definitions? Okay, so that's us practicing with the ideas of basis. All right, now that we have the idea of a basis for a space, and then we can count those to find the dimensions of a space, we're going to use those to kind of make a really important theorem here for linear algebra. So the dimensions of the column space of A has a special name. We call it the rank of A. So the rank of A is the dimension of the column space of A. So the rank of A is a number. It's 2, it's 5, it's whatever that dimension of that space is. The other important thing is the dimensions of the column space and the null space are related, which is kind of a weird thing when you think about it, because the column space and the null space are both subspaces of different spaces. Right, if A is an m by n, like this, then it takes vectors of size n and maps them to vectors of size m. So it's a transformation. A is a mapping from R n to R m, which means the column space is a subset of Rm, and the null space is a subset of Rn. But somehow the dimensions of the column space and null space are related. And this is how they're related. So if I take the dimensions of the column space plus the dimensions of the null space and add them together, I always get n, as in the number of columns of the matrix. It's one of those theorems that's kind of like, huh? Look at it a couple times, but it turns out to be very useful. And we can add those things. So we'll give a little justification of why. All right, so I have a matrix. We'll call it a 1, 2, 3, 1, 2, 3, 4, 5. Call it a 3 by 5. Now the way we're going to justify this is really in terms of the variables. If I have a 3 by 5, how many variables am I working with? 5 variables, right? If I set ax equals b, this x would have to be x1, x2, x3, x4, x5. Okay. Now the dimensions of the column space is the number of those columns that are linearly independent. And to figure that out, I row reduce the thing and I mark the pivot positions. I mark the pivot columns. So let's say I have a pivot column here and here. I have leading ones there and there. Those are my 2 pivot positions. Those are essentially marking out my fixed variables. So I have 5 variables, and all the ones that are fixed, those are really marking out the linearly independent variables, and that's really going to be the dimensions of my column space. Okay. So in that sense, the number of fixed variables is really equal to the dimensions of the column space. Now if I look at this as the homogeneous equation, this thing equal to 0, and these other variables are going to be my free variables. And the free variables we're looking at the size of the null space. Because these two values are fixed, they're perfectly defined. You almost think about it, if they were all defined, well then the size of then I would have x1 equals 0, x2 equals 0, x3, and those things would all be defined. But if I have one free variable, I'd have all the rest can be 0, then I'd have this free variable. I'd have some multiple of some other vector that would all map to 0. So if I had two of them, I'd have some multiple of one vector plus some multiple of another vector. That would be a linear combination of those two vectors that would all map to 0 if those are solutions. So it's really the number of my free variables that tell me my dimensions of the null space. Then of course the number of fixed variables plus the number of free variables must be the number of total variables, which is n in this case. That's kind of a quick justification of why this might make sense. All right, questions so far? Must be harder to concentrate the better the weather gets, right? Is that the rule of thumb? Start doing something in class like jumping jacks in the middle of class or something. Start blood flowing a little bit. Okay, another clicker quiz. So now we're going to try to see if we can identify all these pieces. So what I want us to do is put values here, 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 and here. 5 answers. So take your time, write all your answers out, do whatever you need to do to think about this one, and then we'll go through and I'll ask what value goes here and so on and so forth. We'll start the first one and we'll go with this one first. So A is a mapping from R here to R here. What's the first one? Pretty mixed here between C and E. All right, those are the two we should be mixed with. The question is, when you struggle on this one, is if you're to grab a vector, right? Take some vector and write it here, and ask yourself how big does it have to be for me actually to do the multiplication. All right, if this was 3, that means I would have x1, x2, x3. Can I do that multiplication?
No.
I can't. I really encourage you to write it out. x1, x2, x3, x4, x5. That's the size it has to be to do the multiplication. That's really what this transformation is doing. It's taking the x vectors and mapping them to b vectors. It's taking things that live in R5. So this one is R5. And it's sending them to vectors of what size? So this thing is equal to some b. How big is b?
5 by 1.
So new clicker quiz. Mapping R5 to R3. It would be B1, B2, B3. Because when we do this multiplication, one way we can think about the multiplication is x1 times this first column, plus x2 times the second column, plus x3 times the third column. We're adding up these columns. These are all vectors of 3 values, 3-dimensional vectors. We have a bunch of vectors in R3, we get a vector in R3. All right, what's the rank of A? Let me stop this one and start another one. What is the rank of A? The rank of A, which is the dimension of the column space. Pretty mixed here as well. Mostly C though. I would agree with C. The dimensions of the column space. It's the span of the columns. That's what the column space is. And so I know that if I take a linear combination of these, I get elements in R3. The question is, do I get all the elements in R3? Do I only get a plane in R3? Do I get a line in R3? Do I get a point in R3? That's really the question. And in this case, because I have 3 independent vectors, because if I look at this form, it really is in echelon form already. It's not reduced, but it's in echelon form. So I can mark my pivot positions here, here, and here. It has 3 pivot positions. It has those 3 fixed variables, you can think of that way. And they're really marking out these independent columns. This one's not independent. It's just 2 times the first one. Right, so that one's not independent. This one, I might not be able to see exactly what linear combination is, but because I've marked my pivot positions, there's some linear combination of this vector, and this vector that will get me this one. So I don't need this one. So I have 3 independent vectors in R3. And that tells me that they're a basis. Right? They're definitely going to span the space because I have 3 linearly independent vectors here. So in this case, it's going to be 3. The rank of A is 3. 3 basis vectors here. All right, stop that one. We'll go to the dimensions of the null space. What are the dimensions of the null space? Two. 2 is correct. Why 2? Well, there's a couple ways. I know the dimension of the column space plus the dimension of the null space should give me n. What is n in this case? 5. Right? So I know this is 3. I know 3 plus this number has to equal 5. This has got to be 2. That's one way I can think about it. I can also think about it as those are marking my free variables. I could also just take this matrix and look at the homogeneous equation and find the solutions. If I did that, if I take this and finish the row reduction and write out my solutions in parametric form, I would get something that looks like this. x2 times some vector plus x3 times some vector. This tells me that the solution space, the set of all solutions, is really a linear combination of these 2 vectors. Well, the solution space to the homogeneous equation is the null space. And because I can form it as a linear combination of these 2 vectors would be a basis for the null space, would be a basis for the solution space. Okay? So once again, here I want the dimension. I can get the dimension very quickly, but I could actually form that solution space by solving that homogeneous equation. And then lastly, the rank of A plus the dimension of the null space, that should be 5. We had that theorem. Okay, questions about this problem? Okay. So now we got to tie this back in some stuff we already know. For A, which is an n by n, that's an important qualification here. To have an inverse, we must be able to row reduce to identity. Thus, if A is invertible, we're going to know some things about the dimension of the null space, all these things. So that invertible matrix theorem that we already had that already went down to like L or something, it's going to go down farther now. Because saying the matrix is invertible for an n by n is really the same thing as saying these other things as well. These are more things that are going to be tied together in that giant list of criteria. So I have n. It's an n by n matrix. And we'll call ours a 3 by 3. And it's invertible, which means when I do the row reduction, when I put it in reduced row echelon form, it's going to look like this. So in that case, what would the dimensions of the null space be? Zero. What is the null space? Zero. It's the zero vector. If we have just the zero vector, we call the dimensions of that space just zero. What would be the rank of A? The dimension of the column space? 3. We're just counting the pivot positions there. Or more generally, it would be n. And what about the column space of A? What is the column space? Because this is invertible, we know it has to be 1-to-1 and onto. So what is the column space? Is it R3? Or in general, Rn? Once again, because all these things are interconnected. If it's invertible, it's 1-to-1 and onto. If it's onto, it's spanning the space. If it's spanning the space, then the column space is not just a subspace of R3, but it is all of R3. All these things are interconnected here. Okay. All right, so why do we care so much about basis vectors? We spend a lot of time talking about basis vectors. They're the building blocks, right? They are the smallest number of vectors that you can use to generate any other vector in the space. Given a basis vector, or basis, or a space V, each vector in V can be uniquely represented as a linear combination of the basis vectors. Remember, uniquely because they have to be linearly independent. So if you give me some x vector that's in our space, and you give me some basis of vectors, here's my basis vectors, there is only one linear combination that will map to x. Right? If this is 2, 1, 3, that is the only way I can get to x, is with the 2, the 1, and the 3. Okay? Well, if we define our basis vector and we just let that basis vector sit there and it's well known, then if we want to talk about this vector, we don't have to talk about the vector, we can just give its coordinates. We can just talk about the spot. How do you get to that vector is really the same as the vector if there's only one way to get to the vector. So if I'm talking about this vector, I can talk about its coordinates and just give a list of these coefficients. Say the coordinates of this vector are just, here are the coordinates. Now notice when I write this notation, I have my square brackets. It tells me I'm using coordinates to x. But I also have to tell you what basis I'm using. Because there are more than one bases for a space. I mean, just think of R2. Here's a basis for R2. This is, in fact, my favorite basis. Those two vectors are linearly independent, and they span R2. But here's another one. Certainly another basis. They're linearly independent. They span R2. So they're both bases. So when I talk about the coordinates, I'm talking about the coordinates in a specific basis. It says if you're going to use this as your basis, these are your building blocks. The coordinates are how you use them to build a specific vector. We'll do one quick example and then we'll finish up this discussion tomorrow. In R2, we often don't distinguish between points, coordinates, and the vector. Right? We say 4, 3. Was that the point 4, 3 or the vector that goes to 4, 3? Whatever. Okay? But really when we talk about these points and these coordinates, we're saying let B, my basis, be 1, 0 and 0, 1, my favorite basis, what we call the standard basis. And if I have a vector which is equal to 4, 3, and I want to find the coordinates of x in terms of my basis, I need to find an x1 such that x and x2 such that x1 plus x2, this gives me 4, 3. That's how I find the coordinates. And of course, to do this, we would write out the augmented system. In this case, the augmented system is awesome. And so I know x1 is just 4, x2 is just 3. And so the coordinates in terms of space are just 4, 3. That's why we don't distinguish between the vectors and the coordinates, because they're really the same here when we use a standard basis. But I could certainly give you that other basis, that basis 1, 2, and 1, 1, and say, what are the coordinates to 4, 3 in terms of this basis? And it's just a different way to count. And sometimes, depending on a physical problem, a mechanical system, it might be more useful for us to use these basis vectors instead of our standard ones. If we have some sort of rotation or shift, it might be easier for us to work in different basis vectors. Kind of change our coordinate system instead of just changing our vector. Okay, so the reason we want to talk about bases is because we can use them to generate coordinates. We can use them to describe our whole plane system. All right. All right, so this process tells us how to find coordinates we need to. Later on in chapter 4, we do 4.4 and 4.7. We're going to talk about how to change basis from one basis to another. We'll talk about that next time. So for next time, review our sections we covered in chapter 2 and also read section 4.4. And we'll answer questions and go through that. And that's all I got.